Done. Thank you for reminding for recording.
Okay, guys, right, it's 10:05 exactly, so let's make a start for my bit of the revision section. Before I do anything, can I, and I'm sure it applies to Tatiana as well, be clear? We have given you advice onto the areas of the syllabus you should concentrate on for this exam. And in my case, it's image processing and digital neural networks. Now, that doesn't mean you completely ignore topics that aren't under those headings, because we may well include information, say, on analog neural networks in the discussion on neural networks. So the principal focus is going to be on image processing and digital neural networks from me, but it doesn't mean to say it's going to be exclusive on those. So make sure you are familiar with the broad principles across the whole course. And I hope none of you are going to have to do a resit on this paper or this exam. But if there is a resit exam, we will give you advice on the emphasis on that paper, and it will be different from this one. So don't neglect large chunks of the syllabus. Have an understanding of all of them. Now, right, the first one was a digital neural networks question.
John, just can I just add? From our experience running this module with John, every student who have been attending our lectures, normally they pass. So the students who have problems to go to resit, it's the students we haven't seen very often.
Right. And also I'd like to add, this year, we are going to, at least I'm going to, and Tatiana, both of us, are going to require you to generate your own data so that you'll be working on common problems, but you will be doing different, applying it to different data. It's a bit like the level 1 assignment, if you remember back that far. And so be prepared to have to generate your own data. Now, if there's any doubt as to how you should do that, as long as you end up with a set of data appropriate for the problem, which is different from somebody else, then that will be valid. Because last year when we had the exam, we didn't have time to sort out things online, and we set a classical paper with fixed applications, and it was surprising some of the results we got back. If you are going to copy, don't leave the person's name who you are copying from on the paper you submit, because that incriminates you completely. In terms of exercises, look at all the image processing past questions and the digital neural networks questions. They will be typical of what you're going to get from us in May, next month. But the applications, last year we gave a common application which everybody did. This year you will be working on different data. So that's the main difference. Okay.
John, Jason was asking to give example how we can generate on data. So at least one way how we generate this. We will need student ID to do this.
Yeah. Your student number has 7 digits in it, 7 numbers. So if I was making up an image of 16 pixels, instead of giving you a set of grey level values, I would say take the grey level values for the rows or the columns from your student number. So you would each have a different image to process. Okay?
And
it's going to be fun.
Yeah.
It's going to be fun.
And similarly, just basically make sure that we cover up this topic. Similarly, it will be on my questions. For example, the question which we just covered in previous hour. So you have 7 digits, and I can ask you, for example, generate decimal digits for inputs using your student ID number. So instead of 0.1, 0.9 input was given, I will be asking you to use your student ID number to generate these inputs.
Yeah, and at all times, show you're working. Tell us what you're doing. Tell us what you're thinking about, because mistakes in arithmetic are not really important. You can get 30% of the paper wrong and still get you first. So
yeah, remember, write down all workouts. Don't write the answers only. Write down what do you calculate using calculator.
That's absolutely correct. Okay, I think that's all I want to say about the exam. It's going to be fun. Don't worry, guys. Right, somebody was asking a question on the digital neural networks. And the first one, this was last year, it was question 6, and it was 2020. And the first question was justify a logic function as a neuron. Oh, I can't write, goodness me. And really the explanation goes back to very first principles. Take a natural nerve cell, and it is something like this. And there is the output. These are the inputs. And so we can have values I1 to IN. That can be represented as a vector I. They are combined in some way, and they produce an output Z. Now, if you look at the electrical activity either on the input or the output, we get activity which is something like this, is voltage against time, supposing it's the information on here. We might get a signal that looks like this, and all of a sudden we get a lot of voltage activity, and then it goes flat again. And this is happening on all the inputs and the output. Now, to justify using a logic function, let us say this nerve, or the input nerve or the output nerve, has 2 states. And we would say this is firing. Well, come on, right. Somebody said my whiteboard was behaving itself. Oh, come on, you stupid thing. Why isn't my pen working? That's crazy. That is crazy. What's happened now? Oh, come to my office, folks. It's so much easier. Oh, let's see if I can reload the damn thing. Yes, back to normal. Don't know what happened there. Right. That was the voltage activity, and the voltage is not particularly high. The voltage can be about 100 millivolts. And if we call this firing, and we call this not firing, which the medical profession will agree with, engineers and doctors don't always agree, but they have a sense of superiority, which is misplaced, but we will agree on this. If we have essentially a 2-state activity, why not call this naught, and why not call this 1? So firing is state 1, and not firing is state naught. Going back to our model, if we therefore have binary information on the input, we can represent those as noughts and ones. And of course, they will change with time. And the output is also going to be binary. The question then is, what candidate functions can relate the output to the inputs? And the obvious one is a combinational logic function. Oh, you haven't gone again, have you? Oh, I am touching something that's not working. Why does my pen keep going? Oh. So the candidate operation in the cell is a combinational logic function. So let's now consider a very stylized picture. So this is the letter T. This is another letter T with a sloping top. And there is a third letter T with a short vertical. All of those I hope you would recognize yourself as being the letters T. If we now take these as an input and we take a logic function, which is a model of a neuron, which is sampling the input state, say the top row, and has an output there. We can implement the logic function obviously as gates, but we want programmable logic because we want this to train as we show it patterns to develop a behavior. If this is a random access memory as a logic function, then it would be 8 bits. There we are, and these would be addresses 0, 0, 0 and 1, 1, 1. And if I were to train on the first letter, T, let's assume the cross is 1 and the blank screen is 0. The input here would be 1, 1, 1. No, don't! Oh!
It's John, are you sharing the screen? Because we can see you perfectly right, but based on your reaction, I think you lost whiteboard.
I've lost it, yes.
I was wondering if it has been shared. So now we don't see your whiteboard.
No, it's coming back now. Should be there now.
No, not yet. Yeah, now it's there, yeah.
Right. So, good, okay. Right, so if we're training on this first letter T, the input here will be 1, 1, 1. If I call the inputs A, B, C, then if I'm using a memory to implement this function, I want it to respond when it sees 1, 1, 1 at the top. In the memory, a 1 would be set in that location, having cleared the memory initially. The function is going to be f equals A and B and C. So there we've got a simple gate detecting all ones on the top row. If, however, I add a second pattern, and the second pattern doesn't have a cross there, it has a cross down there. Now we are now seeing 1, 1, 0 being sampled. If it hasn't been trained on this pattern, it would access the memory location 1, 1, 0. It's a 0 and a 0 would come out. But if you train on this pattern, the memory function, the input 1, 1, 0 is a valid f equals 1 term. The memory requires a 1 in that location. And this is really all level 1 digital logic, it's all simple stuff. The function now oh, you bloody thing. Got it back. And I've lost my pen again. Oh, this is going to be interesting recording for you guys to look back on.
I don't know if it's with everyone else because I see the screen which doesn't change at all. Guys, is it the same for everyone or it's only me having bandwidth issue?
I think he's just sharing the application and not the screen. And I think he's clicking on the desktop icon, which is...
John, can you try to share the screen, not application, please?
Right. Share. Let's get rid of that. Window. Have you got it now?
Yeah, we can see. Yep.
You've got it now. Oh, right. And I can write on my pen. Yeah. Gosh. Okay, 110, a new term. We train the network. The function now becomes f equals a and b and c, or a and b and not c. Yes, you can minimize it, but don't bother. Now, that is revealing a fantastic property, because we trained initially on this pattern. We got a response, certainly from the top row. There will be functions looking at the other parts of the image, of course. We now train on the second pattern, which is 110. We add a term to the logic function. You still hearing me? Good. And we do not lose the response of the first training pattern. And that's a completely different behavior from what you get from an analog neuron. And remember, the analog neuron has weights, and they go into a summer, and they are then thresholded. And if we draw that in 2 dimensions, what we have is a pattern there, and a weight vector, let's call that x, and maybe a weight vector there, which will be the coordinates on the axes. Now, if I were to train on a second pattern, down there, I would move the weight vector, and it may well give a different classification to the first pattern. So in getting subsequent patterns correct, you may introduce errors in earlier patterns. And that is only solved by an iterative training process, which can be incredibly long and sometimes won't converge. So back to my digital model, training is additive. And of course, if you want a set diagram for that, what you have is a training pattern. If you add 2 training patterns, it will generate a cluster around that. And that will be your generalization set. And of course, the generalization can grow until, hopefully, to solve a problem, we have a data set which contains all the patterns of the class you're looking for. If G, the generalization set, matches the data set, then you've got a very useful strategy. But the key thing is, it's a logic function. We are adding terms to the logic function as we train, and we don't lose the previous terms. So there's no error correction to be done. And that really is more than enough to get full marks for that part of the question. Then it goes on to applying an application. And I think my training set was in the question. I think we had this pattern here. And this pattern there. If those aren't the exact correct ones, then they will do. And our system was looking at the input space. We had 3 logic functions. Logic function 1, logic function 2, and logic function 3. F1, F2, and F3. And to get an overall response, let's sum them. Summation, and a threshold if needs be. And the connections were row by row. And the way you connect it up is a variable. So you can have different systems with different performances. And the third one in here. So there's your structure. And of course, these are going to be 8-bit memories. You're using RAMs as logic functions. Oh gosh, can't spell memories right, dearie me. IES. And let's see if I can just put the contents in here. I want 8 cells, so there we are. 8 cells, 8 cells, and 8 cells. 1, 2, 3, 4, 5, 6, 7, So I've got too many. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 decimal. Right. First pattern goes in, which is this pattern. The first function is seeing ABC. Let's call the columns ABC to identify them. We will get a 1 set in that location. Don't. Second pattern is 0, 0, 0. We will get a 1 in this location, and the same for the third one. And so just putting the addresses for reference, it's going to be 0, 0, 0 through to 1, 1, 1. For the second training pattern, address 3, 0, 1, 2, 3. I didn't put a 1 in there, did I, for the first one? No. 1, 0, 0 for the second one, which is location 4, 0, 1, 2, 3, 4. And for the last one, 0, 0, 0, we've already got it. And for the third pattern, we're seeing 0, 0, 1, which is location 1. And for the second one, it is 2, 0, 1, 2. And for the third one, it is 5, 0, 1, 2, 3, 4, 5. So I think the question asked, what were the logic functions? Don't bother to minimize them. F1 is going to be A and B and C, which is this term here, or that was location 3 is going to be A and not B and not C, or location here, which was 1, which is going to be A, not A and not B and C. Don't bother to minimize them, you're using memories. So that would be the first logic function. F2 was not A and not B and not C, or A and not B and not C. Was that correct?
Oh, I think F1 second one is wrong. It's A, B, and not C.
Yeah, sure. Well spotted. Right. The states for F1 are 7, 3, 0, 1, 2, 3, and 1. It is 7, that's correct. It's 3. Oops. That's a mistake there. It is A and not A and B and C. That's correct, it's 3. Okay. And F2 is going to have 3 terms in it. Not A, not B, not C, or not A, B, C is 3, 4, 5 is going to be A and not B and C. And for F3, the functions are going to be not A, not B, not C, or that term was A, B, not B, C. Now, it might be a mistake there, check those, but that's the idea. And so those were the equations. If we're now looking for, yeah, mistake?
F2, the last one is wrong. It's not A, B, not C. No, it's the other way around. F2, the last.
Back. It's not A, not B, not C. That's
no,
correct.
Not A, B, not C. F2, last one.
F2, the last one.
Yeah,
Let's
it's
check.
not A, B, not C.
Yeah, you're telling me, well done. I'm learning. Not A, not B, not C, yes. Or not A, not B, not C, yes. And the last one is not A, B, not C. If I was doing this, I'd lose a mark there. I'd still get my first, though. And so that is A, not B, C. Okay, now to work out the generalization. And we can have 3 generalizations.
I think you did the same mistake again. It's not A, B, not C.
Oh, crikey. This one, is it? Sort it. Not A, not B, not C, yes. Or A, not B, not C, yes. Or not A, B, not C. Are we happy with that? Yes,
Yep.
great. You're going to be all right. You're better than me at this. Now we come to the generalization. This is the size of the generalization set based on the training patterns. And G, the generalization set, is the product series, I equals 1 to n over little n of ki. Now we need to define the terms here. N is the number of pixels. And in this case, it is 9. There they are, 1, 2, 3, 4, 5, 6, 7, 8, 9. Little n is the sample size, the n-tuple size. And this is 3 because we're taking 3 points to each function. And ki can be described as one of 3 things. It's the number of terms in the logic function, unminimized, or exactly the same, the number of bits set in the memory, finally, it can be the number of different n-tuples. And for the first ki, for the first function, either we can go back to the training set, the number of different patterns on the top row, 1, 2, 3, the number of bits set in the memory, 1, 2, 3, or if you've got the unminimized logic functions, the number of terms, 1, 2, 3. So that will be 3. So in this case, it is going to be 3. It's a product series times the number of bits set in the second, I think, is 3, and times the number of bits set in the third is 2, which means the generalization set is 3 times 2 times 19. So we have a 19. 3 times 3 times 2 is 18. That's correct. So we have a universe. Don't you start doing that. Come down. We have a universe is 512, which is 2 to the large n, 9. We have a training set, t equals 3. There's your 3 training patterns. Where were they? 1, 2, 3. And that logic network will recognize a generalization set of 18. So it is recognizing patterns outside the training set, and that is the key property. I think the question went on to ask response to unseen patterns. And the 3 test patterns were, and the other one was, and the third one was a diagonal line. So taking this pattern first of all and putting it into the network, in fact, we have the term ABC. If I shrink this down a bit, I might get it all on one page. Yes, this first function will respond with a 1. The second pattern is 0, 0, 0, as is the third. Not A, not B, not C. Not A, not B, not C. So we will get 3 1s coming out of the logic functions. They're summed together. That gives us 3. If the threshold is 3, and this is known as AND threshold, because every input has to be a 1 for the output to be 1, which is 3 out of 3. That pattern will be classified as being a member of the same pattern as the training set. Okay, it has the common top line, it has nothing at the bottom. There are some justifiable similarities, but remember this is very low resolution. Second pattern, the score here is not A, B, C, not A and B and C, 0 comes out. The middle way is A and not B and not C. Is it in that term? No. And the third one is not A, not B, not C. So this will give a score of 1 out of 3. And that won't be recognized for the AND threshold. And the third one is, in fact, I'll check it on the memory contents rather than the logic functions. You can do either. We're seeing 1, we're seeing 2, and we're seeing 4. Are we seeing 1 in the memory? Got spread it out. Location 0, 1. Yes, we got a score of 1 there. Are we seeing 2 here? 0, 1, 2. Yes, 1 comes out. And 4. I think that gives a score of 2 out of 3. Whoops. Come back. So that'll be 2 out of 3. And with an AND threshold, it will not give a response overall to the pattern. So we've got 18 patterns, of which the 3 training patterns are 1, and this one is another one. There's another 14 which the net will respond to. So that's the learning behavior. It's extending to patterns other than the ones it's being trained on. And it does have this beauty, this absolute superb property, that as you train this system, you do not lose the response of earlier. So it's a single pass training. And of course, this can be scaled up. Instead of 3 by 3, this can be 512 by 512. You can have a megabit of memory there divided into 32,000 individual functions. And hey presto, you've got a fairly big system that works on the same principles. Now, I think that covers question 6. Any questions? Silence. Everybody's gone to sleep.
Could you elaborate on
Oh, there you go.
Go on.
Just because the exact question says what is the size of the AND generalization set and the OR generalization set, so I didn't quite
yes.
catch that.
And generalization set is 18, yes?
Yeah.
Okay, yes, I'll do the OR for you. G-OR. Now, G-OR is the same as, going back to the original concept, if I had, instead of this summation and threshold, if I had an OR gate in here, the output would be 1 for every combination of ones and noughts on the outputs of these functions, except all zeros. So a threshold of 1 will pass every pattern that gives at least an output of 1 here. So it's an output of 1, an output of 2, and all 3 functions giving an output of 1. Now, in this example, there would be several combinations of that happening. With a larger example, the number of different inputs you can have to an OR gate to give the output 1 becomes increasingly large. So bear that in mind. So G-OR could be calculated, the number of patterns giving 1 out of 3, the number of patterns giving 2 out of 3, the number of patterns giving 3 out of 3. But a better way is to calculate not G-OR, the patterns not in the G-OR set. And not G-OR is going to be the product series, same counters, I equals 1 to n over n, which in this case is 1 to 3. And this time it is going to be the product series of 2 to the n minus ki. And 2 to the n n, remember, is 3. I defined 3 up there, back there. Where was it? Well, it's obvious n equals 3, the sample size. There it is. Two to the n is the total number of different patterns that can be input to the logic functions, i.e. the number of cells in the memory. In this case, n equals 3, 2 to the n is 8. There's 8 cells. And what we're doing in this part of the equation, we are calculating the number of patterns that will output a 0 rather than a 1. And if we have 0 coming out of the first function, 0 the second function, 0 the third function, then it's the only pattern, only output condition that will not give a threshold of 1, i.e. it's the only input pattern which an OR gate gives an output of 0. So we've calculated the patterns that are not in the generalization set. And in this case, it is going to be the first function, 2 to the n is 8. 8 minus 3 is going to be 5, the same for the second one, and the third one, 8 minus 2 is 6. So not in the generalization set is going to be 5 times 5 times 6 patterns. And that's 6 5s are 30, 3 5 30s is 150. But that is not GOR. We want GOR. GOR must be the universe minus not GOR. And therefore the universe is 2 to the 9 minus 150. And 2 to the 9 is 512 minus 150. So the number of patterns in the OR generalization set is, so work it out yourself, it's going to be 2, 362, is it? I think that's correct. So a much larger generalization set. So another interesting property, we can control the generalization set in these structures with this output threshold. And in this very simple example, you've only got 3 conditions. You've got G AND, you've got G OR, and the other one would be G for the threshold equal to 2. And if you wanted to calculate that, you'd have to work out the number of combinations of getting 2 out of 3. But in practice, real systems, you'd never use G AND, you'd never use G OR, you'd have a variable threshold which you can control the actual capture of patterns. So that's the G OR. Have I covered all the points in that question? Right, now if that was yeah, go on.
No, yeah, you've covered all the points of the question.
Great. Now, if that was a question this year, it would be exactly the same type of problem, but instead of me giving you this training set, as I did last year, you would have to make up your own training set. And I would give you a set of rules for doing it, and you'd have 3 patterns again, but each of you would have different patterns. So the principle would be exactly the same. Work through it, understand the methodology, and you'll all have different answers, but you can all get full marks from it. So don't even bother WhatsApping your friend saying, hey, what's the answer? Because it will benefit your friend if he or she does it for you, because they'll be doing 2 problems and be better than you, but it won't benefit you. Okay, not too bad, is it? Silence. I've frightened you all away, have I? I haven't got the chat up at the moment, so I can't tell what's any comments.
Yeah, that's all right. So for example, say my student number. So would that mean like I generate the data, or would we get instructions on how we can generate the pattern? Because I don't think I know how I can.
You will be getting very clear instructions how to generate the data.
Okay,
So
awesome.
so
Okay.
don't worry about it. And if you make a mistake in generating the data, it won't matter as long as you have a pattern, which is your own pattern. It's the methodology. It's going through this. It's understanding what's going on. This is where you'll get all the marks from.
Perfect. No, it makes sense, and then yeah, I'm looking forward for that. My next
Okay.
question would be, I mean, if everyone wants, could we get a question on image processing? So I was looking at
Yeah,
question number 2 from 2019, and if everyone's okay with that,
right. Can you remind me what the question was?
sorry?
Can you remind me what the question was? I haven't got it in front of me.
Just give me one second. Let me pull up my notes. Okay, so describe a window operator which will high pass filter a digital image. Identify any correction operations required to ensure
Right.
that the filtered image has the same intensity range as the original image. And
High
right
pass.
after that, we have, yep, sorry.
Yeah, okay. Yeah, let's do the high pass filter first of all. High pass filter is a window operator. And the simplest high pass filter is a 3x3 window. And it has weights -1, -1, -1, -1, -1, -1, -1, -1, -1, +8. So it's a +8 in the middle, surrounded by a 8 weights at -1. And what you do is you take an image and you use that window, the 3x3 window, and it moves across the image and it moves down. So you're applying this to every 3x3 part of the image, and the output is the pixel at the center. So that produces an output pixel right at the center. Let's change the color. That point there is the output there. Whoops. So in exam questions, if I'm giving you a 5x5 image to filter, you'll lose the top row, the bottom row, and the sides, and end up with a 3x3 output. Drastic at low resolution, but if you're dealing with 4,000 by 4,000 pixel images, you don't even notice the loss of the top and bottoms and so on. So the key point to understand about a high-pass filter is the limits. Now, if this filter was operating on a 3x3 image, let's take 4-bit resolution per pixel. And supposing the image was all white, so it would be 15, 15, 15, 15. In fact, now I'll use W in the general case. And for 4 bits, it would be 15. So we've got W there, W there, W, 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 W. But supposing, instead of having white in there, let's have black in the center. That will give us the best. Supposing this is 0. And 0 is black. Now, if I'm correlating this window with this fraction of the image, I will get -W, -2W, 3, 4, 5, 6, 7, 8, -8W, and the center is +8W times 0, gives you -8W. Now, if I take the exact opposite of that image, and if I take 0, 0, 0, 0, 0, 0, 0, 0, and the center is W, so it's now a black image surrounding a white pixel. The limit there is going to be no minuses. We've got plus 8 in the middle times w. That is going to be plus 8w. So the limits are going to be minus 8w. Let's call the output pixel is bij. Is going to be greater than or plus 8w. It's going to be less than 8w. It's going to be greater than minus 8w. Now, you might think in that case, because originally taking an image, filtering it, the resolution of the image before filtering has to be the same as the resolution, pixel resolution after filtering. Now, the original image is black to white. It's a grey level image. Be 8 bits for a standard image, 4 bits for an exam question. This, however, will now give a range of minus 8w to plus 8w. We need a range 0 to w. Now, you might think, and I'm not going to write this down because it's wrong, you might think a correction factor would be to take this and add 8w to it, which will give you a range of 0 to 16w, and then divide by 16 and you're down to 0 to w. It would work in principle, but go back to the conditions where you would get these extreme outputs. The minus 8w will occur when you have a white picture with a single black pixel in the middle. And those images there, you can't see those images. If you're looking at the image, you would not see it. It's below the resolution of human perception. And that situation is most probably a dead pixel on the array. So these are insignificant image situations. The other one here is where you've got a black area with a white pixel in the middle. And if we were in class and I was giving this lecture, I would go round and find somebody wearing a black jumper, and I would say, oh, look, there's a white piece of dandruff on your shoulder. You don't want that to come through on the photograph, do you? i.e., it's not a significant image. So instead of normalizing to the limits with high-pass filter, you do a normalization process. And remember, normalization is where we're trying to improve the quality of the image. Get the histogram of the image, and this is going to be the number. This is after filtering, and this is going to be the intensity. And we will have our limits there, minus 8w to plus 8w. And you will have the histogram is something like that. It's obviously going to be digitized. We can identify this 0 will be somewhere in the middle. We can identify this as G min, and we can identify that as G max, the limits. There will be a few pixels down there and a few pixels down there, which cause these limits, and they're likely to be due to faulty CCD arrays. So ignore those. You have to make a sensible judgment as to what G min and G max is. And once you've done that, having filtered the image, then G min to 0. And that is an intensity shift. Where Bij takes on the value of Aij plus K, and K in this case is going to be G min. And then the intensity multiply, Bij takes on the value of Aij times W over G max minus G min. and that will convert this region of the image from 0 to W. So you've got an image within region. If you don't do that, because of these extreme values, the filtered image is going to be in a very limited gray region. So that's high pass filtering. And it differs from low pass filtering. Just to add a comment, this might have been in the question, or it could be. Low pass filtering, the window for low pass filtering is all ones. You're actually smoothing the image. And of course, the limits of that, if the image that window is above is all blacks, call it 0 intensity. So that is going to be 0. If it's all whites, oh, damn it. Oh, don't mess about. Oh! If we taking this, go multiply by all ones. No. That times that is going to be 9W. These are areas of constant intensity. They always occur in every image. So the correction factor for low pass filtering is a simple divide by 9. Okay. Any questions on that? Now, again, if there were a high pass filter image to be filtered, in previous years, I would give you the image and you'd all be using the same image. This year, you'll each generate your own image. So show the working, because I will be marking you on using the correct methodology, and little mistakes in the arithmetic really aren't that important. Okay, guys? Gosh, I've used up all my time.
Yeah, no, but I have to say that it's been helpful because I was kind of lost when I was trying to follow up with the lectures, but I think this revision session helped. I think if you're free for another 5 to 10 minutes, I was wondering if you can get a quick explanation on part B, the numerical.
Part B?
Yeah, the numerical. Apply a high pass filter to the following 5 by 5 pixel image and display the filtered image at 3 by 3 pixel.
Right. Without any... Right. Okay. Let's quickly do that. I'll get you started off. 5 by 5 image. Right. Supposing the image was 4, 3, 2. I'll just do the first window. 1, 6, 5, 10, 12, 13. Right, we're applying the high pass filter image to that region of the image, and the high pass filter is -1, -1, -1, -1, -1, -1, -1, +8. That is sitting on top of here. It will be 8 times 6 is 8. 6s are 48. Minus 4 plus 3 plus 2 plus 1 plus 5 plus 10 plus 12 plus 13. And let's work that out. 4 3s are 4 and 3 is 7, 9, 10, 15, 25, 25, 37, 37, 47, 50. Hang on, that's 50. 48 minus 50 equals, I think it's -2. So the output window after filtering would be a 3 by 3. And this pixel corresponding to the center point there, that window over there, is going to be -2. So that is 1/9 of the calculation. Got it?
Yep, makes sense.
Simple when you know what you're doing, isn't it?
Yeah, simple. But I was wondering, like, is this sufficient for 8 marks? I think I need to go a bit more in depth. But I think it makes sense for me now. Awesome. That's it from my end, guys. Any questions?
I've got to finish now because I've got 2 hours with level 1. Wish me luck.
Yep. Again, we would appreciate if we could get any hints and tips, to our inboxes during the course of the week.
Take us back to
as an icing on the cake.
Ask me the questions, and if my answer is very short, then maybe it's not going to be that relevant. If my answer is detailed, then maybe it is important. Okay?
Perfect, for sure. Oh, just before we end, may I know what day of the week you'll be in on campus? Just if I have any doubts.
I don't know. I arranged it at fairly short notice. If you email me, I'll get back to you and let you know when.
Perfect.
Okay?
Right.
Okay, bye, folks.
Oh, sorry. Oh, could you upload could you upload this onto Whiteboard? I mean, all your whiteboards onto Blackboard.
Yeah, I'll try to. Yeah.
Because I can't find a single whiteboard on Blackboard. So it's kind of
Okay.
difficult to follow with the lectures. If you could just upload all of these onto Blackboard, I think that would be fantastic.
Okay, I'll have a word with Tatiana. She's the boss on this. We'll see what we can do.
Awesome. Thank you so much. It's looking forward for the exams now.
Yeah, just don't give me a reset opportunity. I don't want my summer spoilt with reset marking. Neither do you.
Well, I can guarantee you it's either a first class or nothing. Period.
Yep, that's the way to do it. And the first class is only 70%. Should be quite easy.
It's just 70. Yeah. I'm sure we all can get
Just
that. Come on,
70.
guys. We got the
7
first class.
out of 10.
Let's go.
That's all you needed. Got to go now. Bye.
See you. Thanks again. Bye-bye.